Okay, yeah. All right, we're good. We're going to continue talking about determinants and all the wonderful properties that they have. By the way, if you computed more than 2 determinants for that quiz, you worked way too hard and you should be studying. So for A, you had to do it. I'd expand along the 3rd row or the 2nd row or the 3rd column. B, you would have noticed that the 1st row is just a multiple of the 1st row of A. And so you just multiply that number you got first to get that one. C is another one you'd have to compute, but I'd use like pivotal condensation or something like that. All the ones would kill each other nicely. D was 0 because there was a column of zeros. And E was 0 because 2 rows were proportional. So most of them you didn't have to do. And we know that determinant is non-zero. The reduced or echelon form is always the identity. And right, which means that a system would have a unique solution. Anyway, let's move on. Properties of determinants. Anyway, the answers to the quiz, it's already online, so you can check it out at your leisure. If we get there, I'll also do some of 1.4 and 1.5 in this section, which is talking about inverses, but I feel like some things just kind of naturally segue into me talking about inverses. So I'll just throw them in. Let's recall some facts. A. Remember type 3 operations. How do they affect the determinant? Huh? They don't change. They do not affect the determinant. Right, so that's when you replace one row by itself plus a multiple of another row, then you actually don't change the determinant. Proof of this, not super hard. It's sort of, you can use theorem 3.1 from the text, theorem 2.3.1 from the text. Basically, you can split this matrix into 2 parts, or one of them have determinant 0, and they just differ in the row by that constant. So the idea is the determinant of something like say A11 plus some multiple of another row, AI1, A12 plus RAI2, etc. Theorem 2.3.1, theorem 2.3.1 suggests that this determinant is exactly the same as the determinant that you would get I and J, because we don't know what row this is. AI1 all the way to AIN plus the determinant. And this is RAJ1. RAJ1. Right, there's a theorem in the book. The book called it this matrix C. This was matrix A and B. And it said when 2 matrices have this relationship where they're pretty much the same in all rows, except they're the same everywhere except in one row, then you can sort of do this manipulation. You can break it up into a sum. not going to tell you exactly what it says, but that's basically it. You'll end up with getting this guy being 0 because he's a multiple of another row, which we know that gives you 0. And so a determinant of that is just a determinant of the original. We also remember that type 2 didn't give a full argument, I just started giving you the idea. I don't want to actually spend time proving some of these properties. We'll do some proofs later. Type 2 operations scale the determinant. By the scalar k that is used. So the idea is take one row, multiply it by a non-zero constant, you'd end up multiplying the determinant by that non-zero constant. And to see that, you just expand along the row. And when you do that, you can factor the common k out. And you'd be left over with the original determinant beside it. So that wasn't true. C was type 1 operations, meaning you switch 2 rows, and it turns out you take the negative of the determinant. They negate the determinant. The idea here So the idea is you can actually switch 2 rows. You can actually use row operations to do this, right? So let's say you want row 1 to be switched with row 3. What you can do is you can take row 3, you can add row 1 to it, and then you're going to subtract row 1, the original row 3 numbers from that. So you're doing sort of type 3 operations. At the end of the day, to make everything level, you're going to have to multiply row 3 by a -1. And according to this one, that makes the determinant negative. So we have those. This was all, I wrote this down last time. I just thought I'd talk a little bit more about the idea that's going on behind them. Here's another theorem that follows. A matrix has 2 rows or columns that are proportional, then the determinant is actually 0, right? You can just do a type 3 operation to make a row of zeros and then expand along that 0 row. So knowing these little tricks is what would have helped you on the quiz to get to answers quicker. What else did we do? Okay, we also remember there was another theorem that basically A is an n by n matrix. Then the determinant of k times A was equal to k. k to the n times the determinant of A. Right? Basically, you're applying this theorem over and over, and you keep factoring out a k for every row, and your matrix has n rows. What else do I want to say? Warning, in general, the determinant of a sum is not the same as the sum of the determinants. So don't try to use that trick, it doesn't work. I can give you an example. Okay, suppose A is the matrix 1, 1, 1, 2. B is the matrix minus 1, 1, 1, 2. Then, if I find the determinant of A, that's going to be 2 minus 1, which is 1. And if I find the determinant of B, minus 2 minus 1, that's minus 3. But the determinant of A plus B is the determinant of 0, 2, 2, 4, which is minus 4, which is not the same as minus 2, which is actually what determinant of A plus B, determinant of B is. So watch out for that. Determinants do not respect addition. However, they do respect multiplication, and the proof of that is kind of hairy. No way I'm going to do that, but you can look it up if you like. And we're going to get so much use out of this thing, it's surprising. AN and BN are matrices. Then the determinant of the product AB is actually equal to the product of the determinants. That's an important factor. We're going to be using that all the time. All these are sort of important, but this is one that, but some of these you can derive easily by knowing a few of the other basic rules. This one is not so easily derived, but it's something that you should know. This implies as a corollary. I always spell corollary wrong. I don't remember if it says corollary. Is this an O?
Yeah.
And it has either 2 R's or 2 L's, I can never remember.
2 L's.
It doesn't, whatever. So then, from this you can get that if you take the determinant of a matrix to a power, k, then that's just the determinant of A raised to the k, which is another thing that would have helped you in the quiz when I asked you about that. So that actually, maybe I will do a problem from the quiz, just to sort of apply this. But we're going to apply it in much more important ways than this, but this will save you some work. Oh, to do that I have to tell you about 2 other things. Can you tell about those first? It's another theorem. N by M is a matrix, then the determinant of A is actually exactly the same as the determinant of its transpose. Right, remember what transpose are? Is when you switch the rows and column. Proof that is not hard. Expanding along the ith row, of A would give the same result as expanding along the ith column of A transpose, right? I just turned all the rows into columns. So expanding along a particular row is the same as expanding along a particular the corresponding column for the transpose. So that's straightforward. Before I talk about the next property of the determinant, very, very important definition. And this is sort of going into 1.4. A is called invertible. We're going to talk about invertible matrices. If there is a matrix B n by n such that A times B is equal to the identity and B times A is equal to the identity. In this case, we call B the inverse of A. Or you might see me refer to it as A inverse colloquially. And write this is the notation for the inverse of a matrix, the minus 1 power. Which technically you don't think of it as a minus 1 power, which we'll talk about later, but it's just a notation. Things to note. This is not that. In fact, for matrices, division doesn't make sense, which I believe I mentioned before, but we'll get back to that. Another thing to note, if A no such if A is invertible, it is called non-singular. Of course, if no such matrix exists, then A is non-invertible. Or singular. Just defining some terms here. Another note, AB equals I if and only if BA equals I. So it turns out if you want to figure out if a matrix has an inverse and you think you have a matrix that is its inverse, You only have to check one of these equations. You're gonna have to be throwing out a few definitions for a while, but we're gonna tie this all together pretty soon. Well, hopefully by the end of this class, but definitely by the next class we'll tie a lot of these definitions are gonna come together very beautifully. Talk about triangular matrices. We're going to talk about their determinants and then sort of connect the determinant to the inverse after that. Find the determinant of the inverse and all that. So, matrix is called upper triangular. If all entries below the main diagonal are 0. Example, this is an upper triangular matrix. This is an upper triangular matrix. That's an upper triangular matrix, right? Basically, you find the main diagonal. It means anything that's non-zero will happen above that. If your zeros all below, that's called an upper triangular matrix. Lower triangular has a similar definition. If all entries above the main diagonal are 0. Let me finish our upper triangle. Example. Identity matrices are both upper and lower triangular. In fact, all diagonal matrices are both upper and lower triangular. This is lower triangular. If you look at the main diagonal, above it you have all zeros. Again, lower triangular. All your non-zero elements will occur at the main diagonal or below. here's something that's nice. I don't really call it a theorem. It's not that big of that. If A is an upper or lower triangular matrix, then what do you think the determinant of A would be?
Multiplication of the entry diagonals.
Product of the diagonal elements. Exactly. Proof is not that big a deal. Do cofactor expansion. Always expanding. This is for upper. For upper. Do cofactor expansion, always expanding along the first column. Right. So if you take any one of these matrices and I start to expand along this column, I'll just have the 1 times its cofactor, but these zeros won't matter. And then I keep that cofactor expand along that column, and then the zeros won't matter, and it just keeps breaking down along the diagonal. Whenever you're lazy to show a computation in a proof, you just basically say details left to the reader. Or left as exercise, you make it a homework problem. Alright, so whenever you're writing your math textbook one day, that's how you get out of it.
Can we do that for you?
It's details left to the reader. You basically tell them a sentence what they should do.
Professor, if we do that for a proof for you, can
No.
we work that out? Okay.
Because you're not writing your own textbook, are you? For lower triangle, note a lower triangular matrix. Now you could do something direct like this. You could just always expand along the first row. But you could also notice that a lower triangular matrix is the transpose of an upper triangle, isn't it? And would have the same determinant. It's worth mentioning that the transpose preserves the main diagonal. Main diagonal stays the same under transposition. Corollary. A n by n is a diagonal matrix. Then the determinant is also just the product of the diagonal elements. because it's both upper and lower triangular. So multiply the guys along the diagonal, that's the determinant. Another corollary. Something that you should remember at a glance. The determinant of IN, any size identity matrix, is always a 1. Because the main diagonal elements are 1. So if you multiply the numbers along the main diagonal, you get the number 1. So that's always true. Now this leads us to a theorem. Suppose A n by n is invertible. That means it has an inverse. There's a matrix I can multiply it by to get the identity. Then the determinant of A inverse is 1 over the determinant of A. Very important part. Proof. Since A times A inverse is the identity, because that's what an inverse does, when you multiply you get the multiplicative identity, we have, I can take the determinant of this side, and it's the same as the determinant of that side. As we just mentioned, the determinant of identity is 1. Determinant of a product of matrices is the product of the determinants. Which means I can divide both sides by the determinant of A to get that the determinant of A inverse is just 1 over the determinant of A. Proof. Now, as math people, there should be a knee-jerk reaction that happened to some of you when I did that. What would the reaction be? How do you know it's not 0, right? Whenever you're dividing something, you're like, what if it's 0? That should always be like, you're always worried about that. It's like your worst nightmare is dividing by 0. So yeah, right here I just divided by 0 like it was nothing. How do I know I could do that? Well, let me see. Ultimately, I want to prove a much larger theorem that's going to have this fall out of it. So there are 2 theorems I'm going to want to show. You have all the info for me to show you that yet. So we got diagonals, products of matrices, I told you that rule. Probably tell you about elementary matrices. We'll skip it. Talk about elementary matrices next time. I'm not going to have time to do all the stuff I want to do with them anyway, so we'll leave them out. Here's a theorem. Let A n by n be a matrix. Then the following are equivalent. This phrase, the following are equivalent, is a very important phrase in mathematics. Basically what it means is all are true or all are false at the same time. equivalent means the statements agree in every instance. So once you know one of them is true, you know all of them is true. If you know one of them is false, you know all of them is false. They will all coincide all the time. A. A is invertible. B. The system AX equals B has a unique solution. C, I'm leaving out the elementary matrices one. So the reduce row echelon form of A is the identity. I want to mention it because let me just mention it. I'll tell you guys about this later. A is the product elementary matrices corollary to this theorem is another theorem. Basically says A is invertible if and only if the determinant of A is non-zero. So that's how I know I could divide by the determinant of A, because this fact is working in the background. Now ultimately I'm going to show you both of these, but we have about 10 minutes to go. So let's prove the corollary first. So assuming that all this is true, I'm going to show you this, and then we'll go back and prove it. Because at least I know I'll get through that one. It's relatively a short proof. Assume A is invertible. Then I know that its reducer echelon form is the identity matrix. But we use row operations to go from A to the identity. Row operations only scale a determinant. Right? We have 3 row operations and we know how they all affect the determinant. If we switch to a row, we scale it by a -1. We just multiply it by a negative number. If we do a type 2 operation, multiply through by a constant, then the determinant gets multiplied by that constant. If we do our type 3 operation, it doesn't do anything. It's scaled by 1. Row operations only scale a determinant, which means if the determinant at the end of a bunch of row operations is non-zero, then it was non-zero from the very beginning. Right, so I get to A by doing a bunch of row operations. Well, I get to the identity by doing a bunch of row operations, but the truth is that will only be a scalar multiple of what the determinant of the original was. So that determinant of A cannot be 0. So this symbol is the if and only if symbol. It means you have to prove something in 2 directions. So first I have to prove that if A is invertible, then the determinant is non-zero. And I'd also have to prove the determinant is non-zero, then A is invertible. But it's really just working the argument backwards, so I'm not going to do that. So what I did here was I proved this direction. And I'm saying the proof for the other direction is just a reworking of the same argument. It's not going to be a big deal. So that's that. Some of your heads might be spinning, I know, it's understandable. We're putting together a lot of ideas that we've been talking about for like a couple weeks now. So go home and reread these slowly. But whatever you do, just remember the theorems at least. Like these general theorems that we're using, I'm not going to ask you to prove them, but you should actually at least just know what they say, because we're going to be applying them all the time. So let's start proving the theorem. I'm not sure if we're going to finish it, but we'll pick up next time if we don't. So basically, to prove a list of statements are equivalent, we must show they imply each other. It's basically the strategy. This is how you prove something is equivalent. So here I had 4 statements, A, B, C, D. If I want to prove they're equivalent, what I have to prove is that A implies B, B implies C, C implies D, and then D implies back to A. So once one of them is true, you can literally go through a chain reaction and prove all of them are true. So at any point you begin in that chain, you can link them up, right? So that's basically what we're going to do. So first, let's show that A implies B. I.e., I want to show that A is invertible. Means that this system has a unique solution. So assume A is invertible. Then, if we have AX equals B, what I can do is A is invertible, which means its inverse exists. I can multiply this side of both sides of the equation by the inverse on the left. Now, A inverse times A is just the identity matrix. So it's just IN times X equals A inverse times B, which means that IN times X is just X itself. So X will literally be the product of these two matrices. There's only one of them, because both of these matrices are filled with constants. So I will literally only have one solution if an inverse exists. If the coefficient matrix is invertible, a system with that coefficient matrix will have one solution, which is an answer to the bonus problem in your quiz. So when I ask you how many solutions does this system have, it would be only one, because you proved earlier that the determinant wasn't 0. By the way, I just want to note in particular here, if B is actually the 0 vector, then this says AX equals B has only the trivial solution, which we spoke about last time. Basically, the trivial solution is the 0 vector. Right? Because we know it has only one solution, and we know that the 0 vector solves it, because if you multiply all variables by 0 coefficients, you actually get 0. So if we know that's a solution, and there's only one solution, that must be the only solution. So I believe in your book they actually proved this. They actually proved this case, but it works in general, so I thought I'd show you guys that. Okay. So if the inverse exists, then this system has a unique solution. On top of that, I want to show that I just showed that. So now I'm going to show that B actually implies C. That is, if AX equals B has a unique solution, then the reduced row echelon form of A is the identity. So now I'm going to assume that this has a unique solution. Then it means that this augmented matrix, if I do all these row operations, let's call this P1, P2, is the only possible reduction. Right? Because if I had a row of zeros, I immediately end up with infinitely many solutions. The only way to get a unique solution is if I have a leading 1 in the column of every single variable. Right? And then I can just say this equals that, this one equals that, this one equals that. Right? There's only one thing that it could possibly be equal to. So, the reduced echelon form of A is the identity. And we're pretty much out of time. So we'll stop there. Next time we'll prove that if this is true, then we can write elementary matrices, and we'll start to do a whole bunch of really cool stuff next time, including finding what an inverse is, like how to find it computationally. No homework for next class, but read your notes very slowly, very carefully. try to connect all the ideas I bring together in the